To draw a graph of a logarithm function, we're going to take advantage of the fact that the log is the inverse of an exponential function, provided that the bases match. So I will use the exponential function f of x equals 2 to the x to help me generate a graph of log to the base 2 of x. I want to keep in mind that I can always swap the rows to get the inverse function. So swapping these rows gets me the values that were x values that were inputs to the exponential are now outputs of the log function. So -3, -2, -1, 0, 1, 2, and 3. And the values that were outputs of the exponential function are now inputs to the log function. So 1/8, 1/4, 1/2, 1, 2, 4, and 8. I'm going to plot these points to see what the graph of the log function looks like. Starting with the easy points, I'll start with 0, 1 and go to the right from there. Here is 0, 1, and then 2, 1. Sorry, that is starting with 1, 0 is what I meant to say. Then going on to 2, 1, 4, 2, and 8, 3. I get this downward arc in the first quadrant. As I plot these fractional points, I can see I have an x value of 1/2 and a y value of -1, then an x value of 1/4 with a y value of -2, and an x value of 1/8 with a y value of -3. I can see that these points are approaching 0 with x, meaning that we have a vertical asymptote here at the y-axis. So this is an important characteristic of a log graph, is that it has a vertical asymptote at the y-axis if the graph isn't shifted at all. And it has slow growth in the first quadrant. I can also see the domain from this graph, and that would start at 0 and go to infinity, but it is not inclusive. Because of that vertical asymptote, we don't include 0 in our domain, and the range of this would be all real numbers. So this turns out to be true for any base, not just the base 2. The characteristics that we see apply to any base greater than 1. And bases greater than 1 are the most common bases to see show up in logarithms. So we're always going to see an increasing function with a vertical asymptote at the y-axis and slow growth in the first quadrant. We'll also have the same domain and range, provided that there aren't any transformations applied. Next, we'll take a look at a log graph that has a horizontal shift. So this is the log to base 3 of x plus 5. So from the graph of the log to base 3 of x, this would be basically y equals log to base 3 of x shifted left 5 units. So that we have two tasks here ahead of us. One of those tasks is to figure out what a few points would be on the graph of y equals log to base 3 of x, and the other task is to then shift the graph left 5 units. When we shift the graph, we shift the asymptote with it. So the first thing that we can do is just figure out where that asymptote goes. And in fact, we can do that before we know any of the points on this graph. That asymptote is going to be It's going to be shifted from x equals 0 to x equals -5. So here's -5, and I know that it follows the asymptote down, so I'm just going to draw in this part of it. I also know that the log to any base of 1 is 0, so this intercept here is generally 1 unit over from the asymptote. So let's figure out a few points on the graph of just y equals log to base 3 of x. One of them I said just now, and it might not have been all that clear, so let's say it again. If x is 1, then log to base 3 of 1 is 0. So that means that on my log to base 3 of x graph, I would have a point here at 1, 0. When I shift that over 5 units, just like I shifted my asymptote over 5 units, it ends up still 1 unit away from the asymptote, just like in the original graph. It's easiest to figure out log to base 3 of numbers that are powers of 3, so I'm going to use 3 and 9 for my x values. If x is 3, log to base 3 is 1, because that is the power that I would raise the base 3 to get 3. If x is 9, then log to base 3 of 9 is equal to 2, because 2 is the power that I would raise 3 to get 9. So these are points that are on the original log graph before it's shifted. So let's go ahead and just lightly plot those. 3, 1, and 9, 2 would be way out here. Now I can shift each of those points left 5 units to get a point that is on the graph of my shifted log. So I have one here and one here. So a good log graph is going to have the correct transformations, and it'll also have a few points plotted accurately. I don't really need to worry about getting these fractional points accurate because they're probably not going to be very accurate regardless. At the asymptote, I just need to make sure that it's very clear that my graph approaches a vertical asymptote at x equals -5. And over here, I'm just going to try and make a downward arcing but increasing graph, just like the shape that we've seen in the past. One thing to be cautious about is that graphing calculators mostly do a very poor job of drawing log graphs. So we can't rely on technology for these. We really need to know where that asymptote is and make sure that our graphs drawn by hand reflect that. A fairly common graphing calculator rendition of this would look something like this. The green graph here is what we might see from a graphing calculator. What happens as it gets close to that asymptote is that the graph just vanishes. So it'll look like it just stops at a point here. The reason that happens is that the log graph approaches the asymptote so fast that graphing calculators, with their simple methodology of just plotting points, they usually don't sample enough points to really capture that behavior. So don't rely on the graphing calculator. Definitely know where that asymptote is and know how to draw a log graph demonstrating that the graph approaches that asymptote.